Integrals let us find the area enclosed within any graph. However, people who have watched my original integral video might be wondering how this statement could even be close to true. How could this video teach me how to find an area like this, or like this? There was just no way I could have figured these out from that video. And my official response to that is, who the hell are you, and why am I even talking to myself? Wait, get the hell out of here. Anyways, even though that dude was charged for breaking and entering, let's explore this anyway. Welcome to Integrals Part 2. So one of the most common integral questions you'll run into are areas enclosed with two graphs. Let's look at this example. There are two graphs, x squared and the square root of x, and you're tasked to find the area inside here. So from the previous video, you learned that an integral finds the area under a graph. So if we were to take the integral of the top graph, that being the square root of x, this is the area that we'll find. Now let's see the integral of x squared. It'll look like this. So you'll notice that we already kind of have the enclosed area. We just have to get rid of this bottom bit. But that bottom bit is actually the area under the x squared graph. So all we actually have to do is subtract the area under the x squared graph from the square root graph. So then we have an equation like this. Now since integrals can be split up if they're separate terms, they can also be combined into one integral as well. So we combine it and it ends up being the integral of square root of x minus x squared dx. But wait, we're still missing the bounds. So how do we know those? Well, the bounds are actually the leftmost x value and the rightmost x value on the enclosed area. Since we have dx, we're evaluating with respect to x, so we need to find the rightmost and leftmost points. For us, the enclosed area starts and ends where the graphs cross over. So all we have to do is make these graphs equal to each other and see where the x values are. So the square root of x equals x squared. Now the values that will solve this equation are 1 and 0, so these are the solutions. This means that x equals 0 and x equals 1 are our bounds. Now all we have to do is plug these all into an integral and we get a final answer of 1/3. So the actual antiderivative part and the working out bit was explained in my previous video, so for now I'll just be using a calculator and skipping this step. Let's try another one. We bring back the square root of x graph again, and this time we're finding the area underneath this line y equals 1. Now this one actually trips people up because it looks like you just find the integral of this line, but not really. Now what we want to remember is that the line up here actually also has an equation, that being y equals 1. So the area of this line minus the area underneath the square root graph equals this area. So we just subtract the higher line, that being y equals 1, by the lower line, that being the square root of x. So then we get the integral of 1 minus the square root of x. Now for the bounds, we just make these equal to each other. X is clearly 1, and now the lower bound is where the y-axis cuts off the graph, so 0. We now have the integral of 1 minus the square root of x dx, all evaluated from 1 to 0. This results in 1/3 again. Wow! Now let's look at a different case. Here we have the x squared graph and a y equals 1 line going through it. The area we must find is this area up until x equals 2. So okay, we just have to subtract the top function by the bottom one. Wait a second though, these are both the top functions. How do we solve this one? I'm glad you asked, imaginary me. Let's go through this. Now you'll notice that the top function changes within the area, and that is very important. The total area under the graph is actually comprised of the two top functions' areas. So we just evaluate it with the different bounds, and then we just add them up to get the total area. So to begin, let's find the area under the x squared graph first. We have the integral, but the bounds are x equals 0 and this point right here. Now this point is clearly where the two graphs touch, so again we just make them equal to each other. X squared equals 1, and we square root 1, and we get 1 and -1. Now -1 is not important in this context, so we just omit that, and we have our upper bound of 1. So we have our first integral, and we just add this one up to the second integral. So our integral would be the integral of 1 dx. Now the upper bound from before is now the lower bound, and the new upper bound is just where the question says it ends, which is x equals 2. So this is our second integral, and we add it up to the first one. We then calculate it, and our grand total comes out to be 4/3. Incredible! Now let's move on to the very last question. we're gonna really crank up the difficulty here. We have this monstrous looking area right here. It is comprised of y equals 1/2 x squared, y equals negative x squared plus 4, and y equals 3. All these functions combine for this area to happen, and that's what we want to solve for. Now this seems super daunting, but we can break this down. The bottom function is always going to be 1/2 x squared, so we can just leave that alone. The top function, however, changes once. First, it's the y equals 3 graph, and then after a point it becomes negative x squared plus 4. So you want to find the point where it changes from the y equals 3 to the negative x squared plus 4. And we do that by making them equal to each other once again. 3 equals negative x squared plus 4. So we subtract 4 on both sides and then multiply each side by negative 1, and then we square root to get x equals 1. So that's our in-between bound. Our rightmost bound is when the negative x squared plus 4 graph hits the 1/2 x squared graph. So we make them equal to each other and then solve. For this one, we just combine like terms and then we multiply 2 over 3 on each side to make it 8 over 3 equals x squared. Then we take the square root on both sides and we get square root of 8 over 3 equals x. There's no need to simplify this since we're going to put it into a calculator. Now for the leftmost bound, that's just given by the problem that it's x equals 0. So we have two clear areas, here and here. Starting with the left area, the top function is y equals 3 and the bottom function is 1/2 x squared. This means that our integral would be 3 minus 1/2 x squared. This is evaluated from 1 to 0. Now for our second integral, the top function is negative x squared plus 4 and the bottom function is 1/2 x squared. So once again, top function minus the bottom, giving us the integral of negative x squared plus 4 minus 1/2 x squared. This is evaluated from root 8 over 3 to 1. We then calculate these values and you should get around 3.688 as your area. And that's all there is to it. Thank you imaginary me for asking the question for the integral part 2. Hopefully this helps with the enclosed area questions. This skill is actually super important once you get into the solids of revolution, which I'll hopefully get to soon. So for now, best of luck with your studies and bye bye.